Hi everybody. Apologies for the delay on getting the stream started here. Let me just wind the music down. Lunch went a little long. And by lunch went a little long, I meant mostly that I started cooking a little later than I probably should have. Welcome back to 140. Let's see, we're doing Unit 7 today. We probably won't finish Unit 7, but we'll do a big chunk out of it for sure. Uh-oh. Maya has heard me. What do I want to say about what's going on here? Not really much. So everything that's on the screen is kind of old hat at this point. So there is a quiz due on Tuesday. The lab that we talked about yesterday will be due on Thursday of next week. And you have an exam coming up soon. Let me look at the syllabus real quick. I still have it open. Yeah, your exam is on Monday of week 6. So we're getting pretty close to exam number 1, which is going to cover units 1 through 8. So make sure you're spending your time wisely and studying up until then. Don't study at the last minute. Just like cram all beforehand. That ends poorly. Let me get to the right screen. There we go. Okay. Chapter 7 is all about atomic structure. We're going to learn about the parts of the atom, what makes them up, and what makes them different from one another on the periodic table. We talked earlier about elements and how all elements on the periodic table are different from each other in some fundamental way, and we're going to talk about that today. So I'm going to give you a sample of copper. I don't know why it's blue, but there it is. There's my copper. Let's suppose that that's a sheet or a block or something like that. And then I asked you, hey, could you cut this in half? Well, sure, I could do that. Okay, can you cut it in half again? Yeah, no problem, boss. And then do it again and again and again and again and again and over and over and over and over and over. That gets a little bit more difficult. But in this theoretical thought experiment here that we're doing, at some point you would get to the smallest possible particle that you could call copper. And that smallest possible particle was coined as the atom. Now, this idea came from Democritus. Democritus was a Greek philosopher in ancient times. And he thought, well, I bet that there's some smallest particle that when you cut this in half, what you have is no longer the substance that we're looking at. So if I cut a copper atom in half, I would end up with something different, whatever the parts for copper were. But he didn't know what those were. Is it a timed exam? Yeah, you get I don't remember how much time you get. It changes between all the classes I take. How much time do I give you on the exam? You get 75 minutes. Oops. There we go. All right. So, with this idea in mind, the notion that there is some tiny, tiny fundamental particle that makes up all of matter has sort of been our benchmark. And even today, we still hold this benchmark. So, for example, on the left here, I have a pile of gold. Not really a pile, this is a gold nugget. And then on the right, if you took one of those like flecks of gold, one of the flakes that have crystallized on the sides, and then put it under a scanning tunneling microscope, you get look at you get to see something like this. What this is, each of these dots is an atom of gold, which is kind of cool. Now, why are there like lines in different colors and stuff like that? My best guess is that it's noise, signal noise. But each of those spheres is intended to be a gold atom. Now, why is it gold? Like, is it this actually the color that is being given off by this element at this level? I can't say if it's been false colored or not. But atoms are so tiny that we need like the most powerful microscope, and even then we can barely make them out. If I gave you a single atom of gold, here's how much it would weigh. 3.7 or 3.27 times 10 to the negative 22 grams. A single atom of gold. Which means that you could have, if you wrote out the number, a 1 followed by 23 zeros would be about a gram of gold. That's absurd. All right. Now, as for size, they're even smaller than you can imagine. The nucleus of the atom, which is what we're going to talk about, where most of the stuff is that we care about, is 1 times 10 to the minus 15 meters wide. That is so small. The rest of the atom, where the electrons live, is like 10,000 to 100,000 times bigger. And so what this implies is not just that the atom is extremely small, but it's also extremely small and also extremely empty. This is the only solid component in there, besides the electrons that are buzzing around, which are extremely small themselves. So if I just go boop, 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 there we go. I threw in some electrons. And that last one is the pen. So all of that stuff in the blue region is empty space. So every single atom of every single entity in the universe is 99.99% empty. So don't feel bad the next time someone calls you an airhead or a space case or something like that. We're all space cases because we're all empty space. In fact, if you took all of the atoms of all of the people on Earth, you could cram them into, like, I want to say it's like a teaspoon, because that's how much extra empty space we take up. It's something ridiculously tiny like that. Other interesting facts about atoms and how small they are is that if you were to compress all of the matter in that many people into one space, you get like 1 billion tons. And so something like this does exist. It's called a neutron star. It's just densely packed neutrons. And a teaspoon of a neutron star would be like 1 million tons. So the matter itself is extremely dense and heavy relative to its volume. However, most of that volume is empty. And so these individual atoms, and then by relationship, other stuff that's larger, like, say, us, isn't anywhere near as large as it could be. Imagine getting out of bed in the morning for Chem 140, or in the afternoon, I guess, since this is an afternoon class, and then getting to the computer or whatever. But it was so difficult because you had the density of a neutron star and you weighed 1 trillion tons. Yeah, that was a terrible joke. Okay. All right. What elements do we know of? We know of 118 so far. And what I'm going to do in the chat here is type in this link, which I believe is the correct link. I'm going to check this really quickly. Yep, there we go. This is p-table. P-table is a periodic table that you can just like click on stuff and then explore more interesting details about it. But importantly, it is a link that you can bookmark for this class if you have a folder for that, I guess. And have handy for whenever we do any questions relating to the periodic table, because we're going to do a lot of periodic table stuff. In fact, it's kind of the major focus of this part of the class, I would say. So play around on p-table when you have a time. What sorts of statements have we determined to be true over the years of studying chemistry? So, and by over the years, I mean since prehistory, from Democritus all the way to today. So along the way, a scientist named John Dalton, and he was around in like the, I want to say 1700s, 1800s, late 1700s, early 1800s. John Dalton made some postulates that we're going to study in 161 in more detail, but the short version of this is, for any given element, all of the atoms have to be exactly the same. So therefore, there must be some fundamental part of the atom that creates its identity, or is the cause of its identity. Now, Dalton didn't know what that was. All Dalton knew was that every sample of copper he looked at reacted the same way with oxygen. It didn't matter where he got it. It didn't matter how much he had. It all reacted identically. It didn't matter where he got his sodium. If you put the sodium in water, it detonated. So all atoms of a given element behave the same. When you do a reaction and you combine elements together, you get what's called a compound. And we talked about compounds when we were talking about sorting matter, right? Remember that elements contain only one type of atom from the periodic table, and the compounds contain at least two. When you combine elements together to make a compound, each compound is unique. So, for example, water is unique. It does specific things. When you drink it, it is refreshing. But if you put alkali metals in it, it is explosive. Whereas if you were to drink this one instead, so these are two very different things. If you were to drink hydrogen peroxide, you would get very sick very quickly. Peroxide is extremely reactive, which is why when you pour it on a cut or on like a surface to clean it, or you gargle with it, it just foams and bubbles and fizzes. Peroxide is actually one of those compounds that is so reactive that it would be dangerous because it would just like instantly mutate your DNA. However, it reacts with the first thing it sees, which is not your DNA. It's anything else. Whatever it comes into contact with, it reacts with. And it just decomposes into water and oxygen, and then whatever it reacted with gets oxidized. All right. Now, when we do this sort of transformation, when we add elements to each other, or decompose them, or rearrange them, or whatever, this is called chemistry. So the whole point of this class is to explore how these changes occur. And so you can see on the picture on the right that's very dramatized. Dramatized? I don't know. I'm making up words now. Now, for our purposes in this class, atoms are indestructible. You cannot break an atom into pieces during a chemical reaction. Now, as far as I am concerned, the statement is actually true. So, you can't break pieces off of atoms in a chemical reaction, but you can totally do that in nuclear chemistry. So, nuclear chemistry does not follow the same rules. Instead, you just obliterate atoms by shooting other atoms at them. This is what happens in the Large Hadron Collider in Europe, or at CERN, or particle accelerators, things like that. You're basically launching things into each other as high as the speed as you can, and seeing what you can pick up from the wreckage. In chemistry, the molecules do not move that fast at all. They are moving much, much, much slower. And therefore, they form a different type of reaction, which just involves rearranging things like electrons. All right. Let's talk about the two types of compounds that we are going to examine in this class. The first type of compound we're going to talk about, which we're going to focus on in unit, I want to say 10. Yeah, I believe that's right. Molecular compounds are molecular. Duh, right? But what does that mean? So you can see here that in my sample of water that I've got floating around here, I don't know if that color is going to show up. Hold on. Let's try this. So you can see that each of these molecules is independent of its neighbors. And that if there are two that are overlapping, it's due to perspective. I'm just trying to circle the low-hanging fruit here. Like, oh, this guy's alone. So these are all independent. I couldn't fit the word on the screen. It was going to go off. So independent is what that means. So in other words, those molecules sort of just bonk around, kind of like if you threw a bunch of marbles in a bag. Each of the marbles in your marble bag would move around past the others, but they wouldn't really stick to each other, right? An ionic compound is different. Instead of making a molecule, you make an ionic lattice. The example that we have here would be if you put a bunch of magnetic marbles in a bag. So ionic compounds make crystalline lattices. If you put a bunch of marbles in a bag, maybe you've seen those little tiny, like, I think they're called buckyballs or something like that. But there's all sorts of these magnets out on the market where you can, like, arrange them to make patterns. Or some of them are painted so you can arrange them in a certain way so that you get cool colors. If you were to put a bunch of those just in a bag and shake it, they would all just stick together and find some arrangement. That arrangement is what's going on here in the ionic compound. So we call this a crystal lattice. And the reason that we call it a crystal lattice is because the physical entity that we see is a crystal. So here's my crystal right here. If you've seen crystal anything, so like a diamond or other gems that have crystallized, or even a mineral, like salt would be an example of a crystal. So a salt crystal is just a kind of a cubic block. Like if you look really closely, salt is just a bunch of little cubes. Those are all examples of crystal lattices. And the way that they form is that all of the ions that are involved in the bond, and you can see here that I have a plus ion and a minus ion. More on that in chapter 8? Maybe 9. Chapter 9. When you form opposite charges attract. And they attract to each other and all of the neighbors around them. So like this positive sodium is attracted to everything around it, and it sort of just pulls it all towards it. And so they're all stuck. All those chlorines are stuck to that sodium in the middle. And then all those chlorines will attract a sodium to be their neighbor. And then all those sodiums will attract a chlorine to be their neighbor. And this just goes on forever and ever and ever and ever and ever. And in the process, you make a geometric shape, which resembles a cube. So as long as you remember, molecular molecules are like glass marbles, and ionic compounds are like magnetic marbles, you can more or less imagine their structure if you were to throw them all in a bag. So that's the analogy I use. Now, what exactly is a molecule? A molecule is a collection of atoms that are bound together into a unique entity. Now, interestingly, molecular matter is by far the most common type of non-ionic compound that we observe. So there are very few atoms that exist by themselves as lone wolves. So the noble gases do. And then any elements that are in the solid or liquid phase that are not going to be the ones that we talk about later, excuse me, are considered to be atomic, but as a solid, that doesn't really mean much. So like mercury as a liquid would be atomic. Mercury atoms would bounce around. I just dropped my pen. There it is. Mercury atoms bounce around as a fluid. But iron atoms are all just kind of stuck adjacent to each other because they're a solid. They have metallic bonding. Metallic bonding is weird. We'll talk about it in 162. Most elements stick together for one reason or another. We're going to talk a little bit about that in units 9 and 10. But when you get a cluster of atoms together and they form a unique band, we call those molecules. So a molecule is a collection of atoms that are bonded together. Specifically, we're going to make a definition here that not just bonded, but these are... There's going to be text that appears right there. Hold on. We're going to say covalently bonded. Because anything ionically bonded is going to be ionic. Oh, okay, just a picture. So on the bottom here, I have a bunch of molecules and some various examples of them. So I got hydrogen, which is two hydrogen atoms bonded together, makes a hydrogen molecule. Same for oxygen. Phosphorus and sulfur do this weird thing where they get more than two. They make 4 or 8. Water is a molecule, carbon dioxide is a molecule, glucose is a molecule. Anything that you want to be bonded together can be a molecule. So there's no upper bound to how big something can be and still be a molecule. You can have thousands upon thousands of atoms, and it's a molecule, as long as they are all covalently bonded. Now you'll notice that some of these atoms have colors assigned to them, so that oxygen that shows up in each of these molecules, you'll notice that it's always red. Carbon is always represented as a black atom. Hydrogen is represented as a small white atom. And then phosphorus and sulfur, though I don't know if those colors are actually unique. I know sulfur is always yellow. The reason that these colors have been selected is just for identification purposes. There's really no rhyme or reason why each color was given to these things, other than common forms of those atoms may exhibit that color. So, for example, sulfur is just yellow. Like, if you had a chunk of sulfur, it would be very yellow, and you would see, oh, okay, that makes sense. Carbon, one of the most common forms of carbon is charcoal, and charcoal is black. So making a carbon atom be the black sphere is a good representation. But oxygen isn't red. Hydrogen isn't white. Those are colorless gases. Phosphorus typically isn't orange. Like, phosphorus is usually white or red. In terms of like the actual phosphorus matter in the macroscopic world. So some colors are just kind of arbitrary. I think oxygen is chosen to be red because red makes you think of fire, and fire requires oxygen. So that's my best guess. All you'll need to know about the colors is that really just different colors represent different atoms. That's probably good enough. When it comes to molecules, we can categorize matter based on two specific properties. And so the first one is going to be the number of atoms of each type. Oh, sorry, this is going to just be number of atoms in the molecule. The next one is number of atoms of each type. And so, if we have only one atom in a molecule, we'll just call it monatomic. If we have two, we'll call it diatomic. 3 is triatomic, and then so on. This goes up to 6. Yeah, this can go on forever, really. Alternatively, you can just use polyatomic for anything that's got more than 3 atoms. Now, obviously, something that's monatomic is not a molecule, that's just an atom. But we need to put that term somewhere. So we've got number of atoms, and then we have types of atoms. How many different types and number are present in a molecule? So if you only have one type, all the atoms are going to be the same, such as on the left here. We're going to call that homoatomic, because homo means same. If we have different types of atoms in our molecule, like on the CO2 on the right there, we're going to call it heteroatomic, because hetero means different. So every molecule can be assigned a quality from each of those categories. So obviously this one is homoatomic. But because there are 2 atoms, we could also assign it diatomic. Over here, this is heteroatomic because there are 3 atoms, of which there are 2 types. And again, 1, 2, 3, triatomic. So you can assign a category to each of your molecules here based on these 2 properties. So I'm going to give you a bunch of these here to do that. Now, importantly, I have given 6 different problems to do here. A lot of people get confused by these dividers here. So these are just dividers to indicate that there are 6 different problems. I should probably just number them. Maybe someday I will. There you go. So for problems 1 through 6 here, assign a category to each of excuse me, each of these molecules. Now down at the bottom, I stopped drawing pictures of them. I started writing formulas. So do the same thing, apply the rules that we just discussed, and then type your answers in the chat. Be careful about abbreviating in the chat because I'm going to go get some water. And if you use homo to abbreviate, YouTube rather properly thinks that you are using a slur. So no homo, right? Don't do that. I'm allowed to say that because I'm gay. But type out the entire word so that Google doesn't censor you, and then I don't miss it when I come back. Okay, so go ahead and get to work on that, and we'll go over the answers in just a second. All right, about another minute or so to finish up here. Now, when you look at those molecules down at the bottom, 4, 5, and 6 there, treat them the same way as if they were drawn as a picture. So you don't need to know what their shape looks like. You could just, for carbon, for example, you could draw 6 spheres of one color and then 6 spheres of another color for hydrogen. All right, let's go over the answers here. I gotta not use the felt tip pen. There we go. I don't want to use red because most of these are in red, so we'll do black. All right. So here, all of the atoms are the same type. So number 1 would be homoatomic. And because there are 3 of them, triatomic. Over here, we have 5 atoms, but there are 2 different types. So this would be heteroatomic. And you could either say pentatomic or polyatomic. Over here, you can't ever have something that is monatomic and heteroatomic because, by definition, if there's only one type and there's only one atom, you can't have more than one type. Now here I have 2 different elements, which you can see by there being 2 different letters. So this is heteroatomic. Not hetera. Heteroatomic. And polyatomic, because there's like 12 of them there, right? Boop, boop, there you go. Only 2 here, and there's only 1 element, so this is homoatomic and diatomic. That should be an I. I don't know what happened. Oops. I'm the worst at writing. There you go. And then this right here, there are 1, 2, 3 atoms. 2 different types. So this is heteroatomic and triatomic. Oh my goodness. She will not shut up. Hold on. Here, you can talk to the class. Come talk to the class. Tell them all about how I didn't pet you for 45 minutes this morning. Yeah. Oh my goodness. Okay, now you can leave. Go away, Maya. She's mad at me. So why 3 for BeCl2? Because there is 1 Be, and then this 2 says, oh, there are 2 chlorines. Sorry, I guess I'm confused by what the question is that's being asked here. So what is this number down here that that's doing. This is actually why I sort of do these questions. So if I was going to draw BeCl2 as a molecule, it looks something like this. So let's get a color out for beryllium. I'm just going to pick one randomly. So that would be Be. And then I would get one for Cl. And since there are two Cl's, I'll just put a second one in there. That color won't show up. So there we go. So BeCl, Cl. So that's kind of what that looks like. And then you can say, oh, look at this. Yeah, that's probably the best visual representation I can come up with. All right. So that's enough of how atoms and molecules are structured together. Let's talk about individual atoms, like what's contained inside them. And have a bit of a discussion there. I don't have my phone with me. I think I left it in the living room. So I'll go get it when we take our break in like 10 minutes. But someone's going to have to remind me, hey, we're due for a break. So earlier on, we discussed that there are two parts of the atom that we were able to measure. And so one of them was the nucleus, and one of them was the electron cloud. This diagram is really, really exaggerated. The nucleus is made very, very, very big relative to the rest of the electron cloud. And the purpose of that is just so that you can see what the parts of the atom are. So the nucleus is this dense inner region of the atom. So this is the nucleus right here. Everything around the outside of the nucleus is considered to be the electron cloud. So this region around the outside here, I guess I could just color over the whole thing because it'll still distinguish them. So the blue thing is the electron cloud. The yellow thing is the nucleus. Now, even though these two entities are attracted to each other, they don't collide with each other. And so the reason for that is the following. So we know that protons and electrons, or actually, you know what? Before I do this, we'll talk about charge in just a second. Excuse me. Oh, I gotta drink more water. I'm all dry in the throat when I wake up. Yeah, I might have woke up at like 1 p.m. today. That's just what I do. We already know that the atom is much smaller in terms of its nucleus size than this. So let's talk about the parts that are inside the nucleus. So inside the nucleus, you're going to see two entities. So in blue are the protons, and in red are the neutrons. So protons have a property called charge. And charge is something that we just assign symbols to. So we've called protons the thing that has the positive charge. Electrons are the thing that has the negative charge. Neutrons, on the other hand, don't have any charge at all. A neutron walks into a bar and asks for a drink. For you, sir, no charge, says the bartender. Thank you, I'll be here all quarter. Now, these two different charges are attracted to each other. So everything with a positive charge and everything with a negative charge is drawn to each other, kind of like a magnet. In fact, this is how ionic bonds work, right? Everything with a like charge pushes itself apart. So this guy is getting pushed apart from this one, and also from this one. Now, it stands to reason that two things should probably happen here. All the electrons should collapse into the center, And all the protons that are in the middle should push each other apart. But that doesn't actually happen. And here's the reason why. So let's draw this diagram here. In fact, we only need the diagram, so I'm going to do this. I'm going to put it over here, and then when I have to move it around. Oops, hold on. Photoshop, you could at least load correctly when I click on you. All right, so we'll put this over here. So I'm going to show another model that most people are probably aware of. So this is the sun. The sun is just happy to be out and about. This is the Earth. And the Earth is attracted to the sun by gravity. So what would end up happening is that this would get pulled into the sun, and we should all die a fiery death, right? But that's not what happens at all. In fact, the opposite is what happens. We don't get any closer to the sun at all. We stay just as far away from it at all times. Now, if we were to turn off gravity, if I was to go like this, boop, like this, then what would happen is that the Earth would go in its continued trajectory, whichever path it was going on at that instant, which would be perpendicular to the sun. So I'm going to just restore that. But this is the path that the Earth is going at that moment. And gravity pulls it, causing it to do this. Like, you can actually simulate this. So if you have like a yo-yo or like a ball on a string that you like throw for a dog or whatever, if you whirl it around, it will go in a circle because the rope constrains it to a circle. But the instant you let go of the rope, the ball flies in whatever trajectory it is. So if you throw it while it's going forward, it'll launch forward. If you let go of it while it's going backwards, it'll launch backward. And if you let go of it while it's about to like turn down towards the ground, it'll just hit the ground. The only way that that can happen is if that some sort of force, and that force in this case is the gravitational force, prevents it from doing that at all given times. And so the result is you get a circle. With protons and electrons that you can see here, I can just put this model right here. It's more or less the same thing. The nucleus is our sun, and the electrons are our planets. And they're attracted to each other, but they're also moving. So the momentum of electrons carries them around the atom in a very chaotic way. Now, you'll notice that I've, in my little diagram there, I'm going to move the diagram over a bit and then redraw this here. So in our diagram, we have our protons in the center, and then the electrons are on constrained rings. Okay, so there's our nucleus or whatever, and then I'm going to put my electrons on the outside. If there was only one electron, let's just move this out of the way. My electron would go around in a circle for the same reason that the Earth goes around the sun. But the second you put a second electron in here, we'll just put it here. Now this guy is going to repel this one away, and it's still going to have all the momentum that it had before. At the same time, this one's going to get repelled away, even though they're being attracted. So the end result isn't that these go on a circle and then like push each other away. The end result is that in 3 dimensions, they start to do something like this. And you'll notice that the path I'm drawing is highly chaotic and irregular. But what you can say about it is that that path stays within, I should get a different color here. It stays within a given area. And that area is the electron cloud. So when we say electron cloud, we literally mean this region of space where electrons can be. They could be anywhere in that space. So our model down here is not very accurate. You're going to see this model just because it is simpler to represent than whatever the hell this thing is that I just drew. But know, when you look at that model, that that's an approximation. And that in reality, electrons can be wherever they want to around the nucleus. And that there is some structure to it, but not like electrons constrained to rings. That's not what we observe. All right. What the heck is the point of the neutron? What do neutrons do? It turns out that protons push each other away because they have the same charge, right? However, there is another fundamental force. I'm going to put an N in here for neutron that attracts these two together. So this is called the strong nuclear force. You don't need to know about the strong nuclear force. All you need to know about neutrons is that because of the strong nuclear force, they hold protons together. So think of them like nuclear glue. Protons would repel each other if it weren't for neutrons acting as a mediator and saying, hey, calm down, it's all right, we can get along. Now, after a while, the nucleus gets so big, like as you go up in the elements here, the nucleus gets so big that with that many protons in it, it becomes unstable. And so after a certain number of protons, which ends up being like 92 or something, atoms tend to not be stable anymore. Now, with regards to our charge here that we identified, the positive and the negative, atoms are always electrically neutral. And so what that means is that the number of protons and the number of electrons are that number in an atom must be equal. Now keep in mind I wrote that they are equal for an atom. I've also italicized it up here. So atoms are electrically neutral. Same number of protons and electrons. Now, if you change that number, you get rid of electrons or add electrons or whatever, then what you end up with is called an ion. So an ion contains a different number of electrons than there are protons in the nucleus. Now, of these two things, it is far easier to change the number of electrons than it is to change the number of protons. So in chemistry, we only ever modify the number of electrons when we do reactions. So electrons can get transferred all over an atom to other atoms, to other molecules, etc. That's a very common thing. That's called oxidation and reduction. When you create bonds, they are involving electrons. The electrons sit between the two nuclei, on average, and provide an attractive force that holds the atoms together. But the protons are locked in the nucleus. You can't reach them. So the only way to make an ion is to change the number of electrons. The number of protons will stay fixed. All right, I think that is a good point to pause for our break here. Mostly because I think the next one is isotopic notation. Yeah, we're going to start doing that in a second. So when we come back from our break here, we're going to continue our discussion of parts of an atom. And then we're going to start showing how to represent atoms symbolically. Okay, so I'm going to set the timer for 10 minutes, and I will see you after that. Yay! Exactly 10 minutes. That very rarely happens. But sometimes it does. And then we're happy. Alright, so let's continue. We're going to talk about what makes an atom a specific element. And that entity is the number of protons it has. So the number of protons is called the atomic number. And the atomic number is always linked to a given atom. So if you have 11 protons in your nucleus, you are sodium, by definition. So you cannot have any other number of protons to be sodium. You have to have 11. If you had 10, you would instead be neon, and if you had 12, you would instead be magnesium. This is how we define atoms because you can't manipulate the nucleus easily. So this is a really painless way to identify stuff, because it's not going to change easily. All right. I'm just giving some more examples of different atoms. Now, if you go to that p-table link that I showed you earlier, you could look at all the number of protons that every atom has, because they're all numbered 1 through 118. On the screen here, I have some symbology that we're going to use. I'm just highlighting that now here. The letter Z is the variable for the atomic number. And so whenever I represent an atom's Z, that's going to be its number of protons. If you're Canadian, what I actually said there was Z. That's the one Canadian thing I don't do. I don't say Z. Mostly because it doesn't rhyme when you do the alphabet song. It doesn't make any sense. QRSTUVWXYZ? No. Fuck off. That's dumb. I'm allowed to make fun of Canadians for that because I'm half Canadian. A is the mass number. The mass number is the mass of all the stuff that's in the nucleus. And so what's in the nucleus? It's protons and neutrons. So we're going to count the number of protons and the number of neutrons and sum them together. Now be careful. It's really common that students will just say, oh, if Z is protons, A is neutrons. No, that's not true. A is both of them. So be careful. Don't make that mistake. Now, remember how earlier we said that protons and electrons are equal in number if the atom is neutral. So if it's an atom. Knowing what Z is will also tell you that the number of electrons in that atom is that number. So, for example, a carbon atom has Z equals 6. Therefore, if the carbon atom is electrically neutral, it will also have 6 electrons present. Now, Z does not tell you anything about the number of neutrons. The number of neutrons could be really any number that you want it to be. So you could have a carbon atom with 20 neutrons, or with 7 neutrons, or with 1 neutron. Some of those would be unstable, though. We're going to talk about that a little bit in just a second. We'll talk about ions in section 7.3, so we'll get to that later. The last thing I want to mention is that if you go to the periodic table, and actually let me grab that really quickly. So we'll go here. My tab fell asleep. That's not the periodic table. There it is. Okay. So if I turn this on, I'm going to just scroll over to this guy right here. So if I look at the periodic table here, I haven't clicked on vanadium for whatever reason. If you look at vanadium right here, there's a number at the bottom here, and you'll notice that it's some decimal, and that no matter which element I click on or look at, can I not select an atom? I just want to kind of hover over them. Notice that they're all decimals, although technetium was in brackets. We'll talk about what that means later. So all of these are fractions. How would you have a fraction of a proton or a neutron? You can't, right? So this number must be something different. That number at the bottom is not A, because A is a whole number. A must be an integer. Will we be given A and Z and asked to find the neutrons? Yes, because you can do that by subtracting. Because if you subtract the number of protons plus neutrons from the number of protons, you are left with neutrons. So if you were asked to find the number of protons and electrons, they would have the same number. So if I asked you, like, how many were there total, then yeah, it'd be double the atomic number. So here I have potassium selected. It is 19 protons and 19 electrons. How many neutrons does it have? We don't know, based on the information that is shown here. It could have 20 neutrons. It could have 21. It could have 19. It could have 55. Who knows? Anything is possible. In order to find the number of neutrons, I have to give you more information, is what I'm trying to say here. All right. How will we represent that information? We're going to do that this way. So we're going to use this specific symbology to represent any element and its protons and neutrons and electrons. Okay. So the first thing that we're going to do is we're going to pick the element that we're going to look at based on the problem or whatever. You're going to replace curly brackets E with whatever symbol you are examining. So for instance, if I was looking at gold, I would replace the whole thing that's written here with the symbol for gold, which would be AU. Okay, so you're just going to completely delete this. You don't have brackets in your answer. It's just that whenever I wrote E by itself, people would just leave the E there. So you're going to just scribble this entire thing out and write whatever symbol you want there. Then what you're going to do is you're going to put as a subscript in front of your symbol that you wrote, you're going to put Z, the atomic number. Once you've done that, then above your Z goes A. That's the mass number. And then later on, we're not going to really worry about it right now, but up here, in this space that I'm drawing the eraser over, this is where charge is going to go. So because the atom is neutral, we don't put anything here. If the atom had fewer electrons than protons, you'd put a positive number here. And if it had more electrons than protons, you put a negative number here. So once you've done these 3 steps, you're all done. What you have here is called isotopic notation. You might see it written as complete isotopic notation or complete chemical symbol notation. Or there's so many different names for this. I just call it this because it's super easy to write. ZAE. Or ZAE notation. I don't know. I have made up that term, so you're not going to see that anywhere else. But I will write both of these, isotopic notation and then in parentheses ZAE notation. So let's do an example. I want you to create the the isotopic notation symbol for a sulfur atom with 16 protons and 17 neutrons. Tell me what numbers I would write and where. I really should hit mute when I'm drinking water, sorry. What numbers go where with my little S here? So I've got the letter S. What numbers do I write in what spots? Not quite. Not 32. The 16's right. We can put that in there, so let's put the 16 down. But A is not 32 in this case. What is it? $33. That's the right answer. How did we get 33? Well, if there are 16 protons and 17 neutrons. There you go. That's okay. It's an easy mistake to make. Now, does all sulfur have 33 neutrons? Or not 33, I'm sorry. See, even I make the mistake sometimes. Does all sulfur have a mass number 33? No. I could have just as easily given you this as a problem. Or I could have given you this as a problem. Like, I could have picked any isotope I wanted to. So the number of neutrons can be variable. And in fact, that's going to be the whole point of what we talk about in a second here. All right, so now what I want you to do, I want you to write the chemical symbol and the Z and the A for each of these combinations of protons and neutrons, or however I've presented this information. I've tried to make it like a puzzle. So the first two are pretty easy. Just make sure that you understand what you are being asked to write down. Look up the symbol on P table and write the isotopic notation symbol for the entire piece of information for each statement, okay? Give you a few minutes to do that and look around on the periodic table, and then we'll go over the answers together. How are we doing? I know that it's kind of impossible to type in the answers. Just type something when you are finished, and I'll know, and then we'll go over the answer. There you go. That works. 1 or 2 more minutes, and we'll go over the answers. All right. So let's go over the answers here. So I want to look at an atom with 25 protons and 27 neutrons. So I need to go to p-table, which I need to actually grab here. So let's move p-table down here to the bottom. And we'll find the element that has 25 protons. So there it is. Boop. And then I got to Alt-Tab so I can get back to the PowerPoint and draw on it. So 25 protons is manganese. And if it has 27 neutrons, 25 plus 27 is 52. So that would be the ZAE notation symbol for this atom. For the next one, I want Z equals 37, so I got to find that. There it is right there. So 37 is rubidium. And then A is 72, so all I do is just put A up here. I have already told you the number of protons plus neutrons. Three and four are a little bit more tricky. If I want something with the same number of protons and neutrons, then that means that I have to have protons plus neutrons equals 36, because these are going to be the same number. So X would be 18. So that means that I have 18 protons present in this atom. So I'm going to find the atom with 18 protons. There it is. So this would be 1836 argon. This bottom one you have to actually do algebra for. So if I have some number of protons and then the number of protons that I have is one fewer neutron than protons, so that would be this. That would equal 19. So if I solve the algebra here, then the atom I'm looking at is an atom with 10 protons. So let's go find that. Boop, there's that. So this atom would be 10 neon 19. And then we could check, does it have one fewer neutron than protons? Well, protons is 10, neutrons is 9, so that checked out. Ew, who thought we would have to use algebra to do this? Well, sometimes you do. All right. Any questions, let me know. Yeah, protons define it. That's right. Because the neutrons can change, and we're going to find that out in section 7.4. We're going to do that next week on Tuesday. All right, so let's go to the next section. Oops, I got to turn off the neon here. Goodbye. Don't mind me, just taking a drink of water. All right. So we have discussed that atoms contain particles in them, protons, neutrons, and electrons, and that some of those particles could possess charge. We said that protons are positively charged and electrons are negatively charged, and that those opposite charges attract to each other, and like charges would repel. Now, we'd already discussed that because electrons are moving so quickly, they don't get sucked into the nucleus and collapse into it, just like for the same reason the Earth doesn't get sucked into the sun. Now, adding all of the charge of an atom together gets you 0, which means that the number of protons and electrons in a given atom are identical. That should all be reviewed. Let's try and apply some of this knowledge now to discover some other interesting properties of atoms, and then the ions that we're going to make out of them. So let's suppose that you could change the number of electrons, because that is something easy to do. If you do that, the substance you get is called an ion. An ion does not have the same number of protons and electrons. So that means they're different in some way. Let's look at the case where you have more electrons than protons. So more electrons than protons would be called an anion. So here's an example. Oh, sorry, it's on the next slide or two. We'll show an example of an anion in a bit. If I have the other case where I have less electrons than protons, that's called a cation. And let me erase this thing so that I can make it consistent. Less electrons than protons. There we go. Now, what this means is that when you start adding or subtracting electrons, you get a charge overall that's left over. So, for example, let's go to the sample problem. Oh, that's not going to be super helpful. There we go. Yeah, we still have this on the screen. Let's get rid of that. So let's suppose that I'm looking at some atom that has 7 protons and 7 electrons. If I was going to put their charges together, I would do this. So here's my protons and here's my electrons. When I add these numbers together, I get nothing. And that's what we expected, right? Okay, let's do that for a different case. So, I don't know, 10 protons and 13 electrons. There's my 10 protons. There's my 13 electrons. I add them together. 10 and negative 13 makes negative 3. So this would be an anion. There are more electrons than protons. So you are simply adding these numbers together. However, those numbers themselves have a charge, so you need to include that charge with them. Okay. And then finally, if I had, I don't know, 16 protons and 14 electrons, I would end up with a positive result because I would have fewer electrons than protons. So what this means is that if you are subtracting electrons, so here I had to take away 2 electrons, I got a positive charge. This makes sense because when you subtract negative numbers, you get a positive result, right? So for example, if the charge on your atom was 0 and you removed 2 electrons, the charge that would remain would be this. So this is removing 2 electrons. It's really easy to get into the mindset that, like, oh, charge is just however many I add or remove, but it's totally not. It's the opposite of that, okay? So be careful and think about it from a perspective of math. Remember that protons are positive and electrons are negative. Count them all up and then sum them together with their charges, and the math will work out, okay? So just be careful, because intuitively, your brain wants to do the opposite. It just wants to count whatever change you're doing and then make that the charge. All right, so I believe that I have a few examples here for that. So I'm going to have sodium, and I'm going to take away an electron. And so what you want to do here is count the protons and electrons. So sodium, I guess we can go back to this again, can't we? Boop. All right, so sodium has 11 protons. And sodium has 11 electrons. And then what we're going to do is we're going to remove an electron. So if I take away an electron, I no longer have 11. Oh, darn it. I erased everything. Damn it. Okay. If we remove an electron, this is where we are. So the charge that remains is positive 1. And so that looks like this. Here's my sodium atom. It's got 11 protons and 11 electrons in its electron cloud. If I lose an electron, now I only have 10 electrons. Because there's fewer electrons, the electrons repel each other less, because there are less of them. And the electron cloud shrinks. You don't really need to worry about the size of the electron cloud in this class. That'll be 161. We're going to talk about quantum mechanics and how changing the number of protons and electrons manipulates the electron cloud. All about that. That's 161. You can do that next quarter, which I am teaching. I think I'm teaching all the 161. So we'll see you for that. Let's do chlorine. Let's take chlorine and we're going to add an electron to it. So first let's write down what we got for chlorine. You know, maybe not right there. Let's move this guy over here. And we'll change it to chlorine. So there you go. So chlorine has 17 protons and 17 electrons. And now what I'm going to do is I'm going to add an electron to chlorine. So I no longer have 17 electrons. I now have 18. So I'm going to add those numbers together and I get -1. There's my charge. And what does that look like? It looks like this. Basically the opposite of what happened on top. If you add an electron, the electron cloud gets bigger because the electrons repel each other and need more space. All right, so there you have it. This is how we manipulate electrons and figure out their charge on the ion that results. Now, when I write the charge on a symbol, where is my cursor? There it is. Let's get rid of all this ink here. You'll notice that I write the charges as superscripts after the atomic symbol. So if I have my isotopic notation symbol, the place that you're going to put the charge goes in this spot right here. If you have no charge, you leave it blank. You could write 0, that is accepted, but it's uncommon. But if there is no charge, leave it blank. If there is a charge, write the number and then the symbol. So for example, if this was sulfur with 18 electrons, I would write that. So this sulfur would have 16 protons and 18 electrons. There you go. All right. Now, why do we care about this? That's right, yeah. So when you have a positive charge, you have lost electrons because you lost something negative. And when you have an overall negative, it's because you gained something negative. Do elements remain the same chemically when electrons are highly increased or decreased? Actually, it turns out that they don't even remain the same when you change this by 1. So elements have a particular chemical affinity based on the number of electrons they have, and there's a certain number of electrons that makes them stable. Oftentimes, that number of electrons is not what it has when it's neutral. This is why elements are reactive. So, for example, chlorine gas is very deadly to you. And the reason for that is because the number of electrons it has in its neutral state is unstable. So it will try and change the number of electrons by taking them or giving them to something else. If the chlorine was in your lungs, that would be your lung tissue, and so that would be bad. But other elements like helium doesn't do anything. Helium is fine with the number of electrons it has. It will bounce around all day, and nothing will happen to it. It's chemically inert. So on this slide, we're actually going to answer that question. So elements and ions behave very differently. For example, at the very beginning of the quarter, I showed you that sodium metal, which is elemental sodium, when you dropped it in water, it would explode. So you remember that from Unit 1 with the scientific facts where I showed you the 3 different versions of sodium being thrown in the water. However, sodium ion, which is what you find in table salt, does not do that. So if you eat table salt, which contains this ion in it, nothing happens. Your tongue does not explode. You do not explode once it hits your belly. Generally speaking, the explosions within your body are kept to a minimum, and hopefully that minimum is 0. Because sodium plus will not do that. So it turns out a certain number of electrons is required to be stable, and any other number is unstable. And there are certain numbers that are stable in the periodic table. And we're going to talk about that in 161, but also very, very briefly when we get to Unit 9. And I think we're going to touch on it a little bit here. All right, so based on the knowledge that we have so far, and what I have shown you about potassium in this class, potassium is found in bananas. But what type of potassium do you find? Do you find K or K+? What type of potassium do you think is in a banana? The correct answer is that we find ionic potassium in bananas. And the reason that we can say that for sure is because remember back to the video where I was doing sodium and then I showed you potassium and then cesium and rubidium and they progressively got more and more explosive. Regular elemental potassium will burn and burned in like that pink color. Ionic potassium does not do that. Yeah, K+ is stable. Now, neutral does not mean stable. Be careful. Because K+ would have these conditions. In fact, we'll get this back up here. Boop. There you go. So K would have this. So it would have 19 protons and 19 electrons. However, K+ would be different. Now remember, if I lose the electron, I have a positive charge. Now, are all ions stable? No, not necessarily. For example, if I had K2+, that would be unstable. But K+ is stable. We're going to talk about why ions are stable later on. So for now, we can really only answer this question by using our observations of things that we've already looked at. But in the next few sections, we're going to discuss how we get to stability when we talk about the octet rule and valence electrons in Unit 9. For now, let's just make some symbols, and we'll try and put the appropriate symbol on our ion that forms. So for this first example, I want you to tell me what ion forms when you take nitrogen and you give it 3 electrons. And so when I say symbol, I mean like chemical notation symbol, except you can ignore this stuff over here. You just want to put, you want to fill in this stuff. Okay. So write nitrogen and then whatever symbol for charge, number and symbol, should form when you add 3 electrons to nitrogen. Write it in the chat. There you go. Now I'm going to write it like this because we put the format is that you put the number first, then the symbol. Saying that's n-3 is fine, but other scientists will laugh at you, and that's no fun. So, other scientists are jerks, by the way. All right. What ion forms when I take away 2 electrons from calcium? Write it in the chat. Very good. Yeah, you get calcium plus 2, or Ca2+. All right. Now let's go the other way. I'm going to give you iron with a plus 2 charge. How many protons and electrons does it have? And as a hint, I will put this on the screen for you. How many protons and electrons? There you go. Very good. Oops, that's not PowerPoint. I was on the other page. All right. So now what I've got here is I've got this giant-ass table that is sort of just all of these questions that I've been asking you. So what I want you to do is if you have paper handy, copy the table down and then fill in the blanks. So write the ZAE notation and include the charge on the ZAE notation. So, oops, that's not my pen. So see how I have included the charge on all of these? Do the same thing for your notations there too. And then fill in all the numbers based on what you see. You're going to have to go to P-table. You're going to have to look up the names. So whatever goes on these spots, you're going to have to find their names to fill it in. Okay? So when you have an ion plus or minus something, how do we know it's taking away a plus or minus charge versus adding a charge? So the only thing that we're doing here is moving electrons. Remember, electrons are the only thing that can be moved. The number of protons is stuck. So if to get to a charge, like suppose that we need to get to a more negative charge, that means I have to add electrons because electrons are negative. If I'm getting to a more positive charge, I have to remove electrons because electrons are negative, and removing something negative gives you a positive. I hope that answers your question. I was a little confused. I'll give you about 4 or 5 minutes to fill out this table, and then we'll go over the answers. I just looked at the clock and realized that we only have 2 more minutes left, so I better go over the answers here. This is the last slide anyway, so that's fine. All right, so looking at titanium, I don't really have a place to put this anymore. I guess we'll just stick this in the corner. So let's get p-table back up here. I forgot to make the sound effect for it. Boop. There we go. So looking at titanium, we've got 22 protons. And with the rest of this information here, I could go 22 titanium. Protons plus neutrons would be my A, so 22 plus 24 is 46. And then protons and electrons added together, so remember that these are negative and these are positive, give me the overall charge. So positive 22 and negative 20 is positive 2. So that's what you should get. All right, let's find Br on the periodic table. Boop, there it is. So Br is called bromine, so we'd write that. How many protons does it have? 35. In order for me to get negative 2 as a charge, I would need to have 2 additional electrons. So that means I need to have a 37 here. For this next one, I need to find the element that has 6 protons, because the number of protons defines what atom you're looking at. Boop, there it is. So this is carbon. If there are 7 neutrons and 6 protons, that means that A is 13. And if there are 6 protons and 8 electrons, the charge is negative 2, because remember, these are positive and these are negative. We really don't need to go to the periodic table for lead, but I'll put it up there anyway. There it is. Bottom number is Z. Top number is A, so A minus Z would be the number of neutrons. So 205 minus 82 is 123? Is that right? I'm trying to do it in my head. And then to get a charge of 4 plus, I'd have to have 4 fewer electrons than protons. Which one are you? Boop, there we go, ruthenium. So there we go, 44. 94 minus 44 is 50. That was A minus Z. And then I have 3 fewer electrons than protons. There's your answers. And that's all she wrote for today. We're going to continue with the rest of Chapter 7 next section on Tuesday. But for now, that's all I've got. So I hope that everybody has a wonderful weekend. Make sure you're studying, because the exam is going to be coming up rather soon. Blink and you'll miss it, sort of thing. And let me know over the weekend if you have any questions about these units, the lab that we assigned this week, etc. I'm happy to answer those questions, either email or Discord. Thanks again for watching. Have a wonderful weekend, and make sure to do the quiz in the lab for next week. Cheers.